let me explain first off what the chain rule is. And you guys remember function composition f of g of x, right?
Yeah,
Do you remember where we decomposed functions and said this could be my f, this could be my g last year in pre-calc?
not enough to be confident in it.
It's like we did it a little bit. It's not super bad. So let's pretend that this is my function. I could decompose this function into the different color. This, which we're going to call u. I'm going to do it a little differently than we did it in pre-calc. And I could say f of x is u squared.
Yeah.
That kind of makes sense. So then f prime of x equals u squared du dx. The theory behind this is if I'm doing dy, I'm trying to get dy dx, right? That is essentially another name for f prime of x. If I do the derivative dy du, that means u is my independent variable. Because dy dx is derivative of y over derivative of x, derivative of independent variable. Well, if I wanted to be dy dx, I would just multiply by du dx. The du's cancel, and I get dy dx.
So where did we get du over dx from?
Du over dx.
Yeah.
So what does that mean? That simply means the derivative of this u function.
Oh,
So applying this, oops, that's not u squared. What am I doing? The derivative of u squared is 2u.
oh,
2u, and then I have to multiply it by the derivative of du dx. So the chain rule effectively says 2 times whatever this inside is to the first times the derivative of the inside. If I actually multiply this out, I guess 36x cubed plus 12x. If I did this, say the old-fashioned way where I expand it out first, I get 9x to the fourth plus 6x squared plus 1. So that's me foiling out this binomial. Taking its derivative, I get 36x cubed plus 12x. I get the same thing either way. That kind of makes sense. We're going to do a lot more examples of this chain rule, but notice how I got the same thing whether I used the chain rule or I expanded it out. We're going to do a lot of chain rules where you can't expand it out. Like this next function. The chain rule is very hard to notate, so you won't find it notated super well in your formula packet of this inside out. Because honestly, you can have chains within chains within chains, and we'll get there. Okay, we're not going to start there, but we will get there. So x of t equals cosine parentheses t squared plus 1. I'm intentionally using the dx dt instead of x prime notation right now, just to again get you used to it. This is the bottom, that's the top. That makes sense? So this was one that's not dy dx, and I specifically wanted to use this notation because of that, just to get you comfortable and familiar with it. The outside thing is a cosine. What's the derivative of cosine?
Uh, Negative.
Negative sign.
Yeah.
So I take the derivative of the outsidemost function. I leave the inside as it is. And then I multiply by the derivative of the inside. What's the derivative of this inside part?
2t.
2t. In this case, I would say equals negative 2t sine t squared plus 1. So a little bit of simplifying. It's not a whole lot simpler, but try to write it in a way that would be used to seeing that. Especially if you have to take this derivative again, because then you've got a product rule to deal with. Next one. So that means take the derivative of this. Okay, what's the outermost thing?
The sine.
Sine. So the derivative of sine is cosine. Leave the inside alone. That's the part that's hardest to remember. Times, what's the derivative of the inside? Plus 1. Usually, it's probably a little cleaner to write that in front. This one doesn't matter quite as much. But writing it in front makes it clear that it's not part of the cosine. The parentheses should make it kind of clear, but it's easy to make that mistake. That makes sense? Okay. Now's where we get interesting. That's not so bad so far, is it? I'm asked to take the derivative. What's the outermost thing?
Secant squared.
Tangent, which is secant squared. Leave the inside alone. Now I start multiplying by the derivative of the inside.
Cosine.
So the 5 is a 0, right?
Right.
Negative sine is cosine. Sine 2t had an inside, didn't it? That's 2t instead of just t. So the derivative of 2t is 2. It's a chain within a chain. So I started with this inside. When I did its derivative, I also had to account for a chain. I've seen ones with up to 5 chains within chains. For the most part, I like to give those to make sure you can catch them. Okay. They are
It could be a lot worse.
what?
It could be a lot worse.
Yeah, it could be. Like this, the hard part of the chain rule is not forgetting to do it. Um, they rewrote it like this. That's the final answer. So you definitely would want to move the negative and the two to the front. They decided it was easier to put the cosine in the front too, which I tend to agree with. But yeah, please don't leave negatives in the middle like that when it's times. Please don't leave these times two at the ends. Okay, finding a slope. Now, last thing about this. In calculus, all derivatives, and when we reverse them, integrals are the reverse of derivatives, need to be done in radian mode. All calculus is done in radian mode. Sometimes they will give you an angle in degrees. You convert to radians, do the calculus, convert back to degrees. That conversion of multiplying by pi over 180 or 180 over pi is easy. Doing calculus in degree mode, harder than those conversions. A lot harder. Like there's just little extra things you have to add. So just don't do it. Pretty much everyone does calculus in radians. The formulas all work great in radians. You have to add little tweaks and adjustments to do it in degrees, and it's not worth it. That makes sense. It's easier to just do the conversion. Honestly, in physics, and I was talking with Mr. Ballsmeyer about this when he was helping me with physics class. He's like, "Oh yeah, I do things in English unit, American units all the time. We take the American units, we convert it to metric, run the equations, convert it back because it's so much easier." Uh-huh. Because those conversions on the end aren't that big of a deal when you're, actually solving a real problem. Yeah, and you won't do you'll do less problems when we get to applications and things because they take longer. You're doing a lot of chain rule problems this week, so you actually get them down well enough to be able to do the chain rule every time it shows up in problem. When it doesn't specifically say, hey, it's a chain rule problem.
Even though,
What?
even though we're check.
Wait. No, you guys have a lot of problems this week. If you didn't look, you have I think you have 37 tonight. No, you have Thursday too. I think you have 37 and tonight and 25 tomorrow. And then you have all of Thursday to work.
We have work day and then we have. Yeah.
And you have the weekend. And once you get going on these, none of these have taken me very long, have they? So this next one says find the slope of the tangent line at the curve y equals sine to the fifth at pi equals 3. This one just asks me for the slope. This doesn't necessarily look like a chain rule, but remember that that's what the sine to the fifth means. And as long as you remember this, you don't have to write this out, but I wanted to point it out, and you might have to write it like that the first couple times. Just remember that, oh, I've got to do 5 sine x to the fourth, bring the 5 in front, reduce the power by 1, times the derivative of sine x. I'd go back to shorthand notation to simplify. Now it asks me for pi over 3. I probably don't want shorthand notation there. Let's see. Sine of pi over 3. Square root of 3 over 2. I know my unit circle.
I know.
You haven't been teaching for 18 years. I don't think I knew my unit circle when I was taking calculus for the first time. I do not think I had that memorized. It would have been helpful, but so square root of 3, that's 9. 45, 30 seconds. Hey, that's right. It also then asked me to show that this has a derivative. Every slope of the tangent line is positive. So here's what I'm about to do. I'm going to make this easier so I don't have to use a quotient rule. Because I'd have to use a quotient rule with a chain rule when I do the derivative at the bottom. Because it's something to the third power. Watch this. How do you like that? Now I don't have a quotient. I can just use a chain rule. What do I still need to do? Multiply by the derivative of the inside. So I get 6. Why is this always going to be positive?
It's the power of 4.
Anything to the fourth is positive. I have a positive over a positive. Always positive. No, are you following? Okay. You have a little bit of a blank look on your face.
When flashbacks and freak out with the long no great proofs. No, this is nowhere near as bad.
Yeah, those are hard. Okay. Do you guys remember parametric equations where you had x of t equal x equals something with a t and y equals something with a t? So I'm going to give you 2 parametric equations. Dx dt would equal what? So I simply take the derivative of the secant squared.
Secant squared or secant?
It's secant t tangent t. Dy dt is secant squared. Guess what dy dx is? It's dy dt over dx dt. Does that make sense where the dt's are going to cancel? And I simplify one of the secants cancels. I get secant t over tangent t, which I think I can simplify more. Secant is 1 over cosine. Tangent is sine over cosine, which dividing fractions, what do I do?
Uh, Slightly.
Apply by the reciprocal. My cosines cancel. I get 1 over sine t, which is cosecant t. Actually, a pretty simple derivative.
Yes.
Getting there was a little bit more work than you probably wanted on the simplifying. Does the parametric thing where I just take dy that part's pretty simple. The simplifying on the trig derivative's a little harder. And they went from here to there in the book.
Oh, they just, oh,
They went from here straight to there. Obviously it does, right? So that's the intro of the chain rule. Tomorrow I should have some time after Abby's lesson to answer questions. Okay. I'm not going to give you more lessons. I will just help you with problems that you're stuck on, as opposed to picking my own problems.
okay.
Okay. Go ahead and try some.